What computations is the brain performing when we look at some lines and curves on a piece of paper and recognize it as a specific word and retrieve its meaning? In this study, we present a large-scale computational model of word recognition and explore what happens when we give the same input to both the model and a volunteer in a scanner. We found that the model can explain three important landmarks in the brain activity. The sequence of brain activity patterns during reading has been the focus of decades of neuroimaging studies. Here, we are looking at data recorded through MEG. The visualization you are about to see shows the evoked response, the average activity produced by the brain in response to 118 Finnish words. There are three components that we consistently see whenever we show written stimuli to our volunteers. The first is a quick and overwhelming burst of activity in the visual cortex, which we will refer to as the type 1 response. The second is a smaller burst, a little further along the ventral stream, which we will refer to as the type 2 response. And much later, much later, a burst of activity in the temporal cortex, which we will refer to as the N400M response. In this study, we sought to understand the computations that are being performed in the brain that give rise to these three bursts of activity. And the way we approach this is to build a computational model that performs the same task as the volunteers in the scanner, to recognize if a bitmap image contains a word, and if so, which word. The model was a convolutional neural network with a VGG11 architecture. It was pre-trained on ImageNet, and then we started training it on images of rendered text until it could recognize 10,000 words with near perfect accuracy. We also included images without any text, containing just the noisy background. And in these cases, all the output units of the model should have a low value. We will be comparing our model to the MEG data collected by Vartiainen et al. In this experiment, they showed the following types of stimuli to the volunteers: valid Finnish words, Finnish pseudo-words, meaningless strings of consonants, symbols that are letter-like but not actual letters, and words embedded in so much noise that they are illegible. The MEG scanner has 306 sensors, recording at a sample rate of 600 Hz. And the model has hundreds of thousands of individual units. In order to compare them, we have to create a summary of this high-dimensional data. For the brain activity, this was done through guided dipole modeling. The three landmarks we are focusing on in this study are represented by three of these dipoles. Here are the locations of these dipoles for each of our 15 volunteers. And below is the grand average time courses at these dipoles in response to each type of stimulus. You can see that each dipole responds differently to each stimulus type. To reduce the time course down to a single number, we take the average activity in a suitable time window. And this is the result. For each stimulus image in the study, we have the amount of activity at each of the three dipoles that correspond to the three landmark locations. Now for the model. We fed the same stimuli as we used in the MEG experiment through the model and recorded the mean ReLU activation in each layer. Note that this is the first time that the model encounters pseudo-words, consonant strings, or symbols. And here is the comparison between the brain and the model. We see that the dipoles that represent the type 1 response react sharply to the amount of visual noise in the image. And we see the same behavior in the first convolution layers of the model. Next, for the type 2 response, we see that it is activated less for noisy stimuli. And interestingly, it is also activated less when the stimuli did not contain valid letters but symbols. It seems that during this response some sort of recognition of letter shapes is going on. And we see this behavior arising in the later layers of the model. At the final 2 convolution layers, we see also a decrease in activation in response to symbols. However, the response pattern doesn't quite match the type 2 response because these layers still respond to visual noise. For the fully connected layers, the response pattern does match quite nicely with that of the type 2 response in the brain. Finally, we have the N400M response. And here we see a distinction between stimuli that are actual words or pseudo-words versus stimuli that are obviously not words, such as consonant strings. And this behavior we see in the output layer of the model, which matches this response pattern quite well. In conclusion, the model I've presented here is overly simplistic in many ways, I know. And yet, it still manages to explain some key observations in the brain activity. I would like to propose this as a baseline model, which we can now build on top of to make it explain even more neuroimaging findings. Thank you for watching, and a big thank you to my collaborators. Bye now.